Hey guys, today's lesson is going to be about writing and balancing chemical reactions as well as identifying the different types of chemical reactions. Um, I would say that pretty much everything in this chemistry unit is important for those of you that are going to be taking Chem 20. So I would hang on to all of this stuff for next year. With that being said, if you're not wanting to hang on to everything, hang on to your notes from this lesson or like save this lesson somewhere, because you like start Chem 20 next year with me expecting that you know how to identify different types of chemical reactions and predict their products and all that kind of stuff. And fairly early on in Chem 20, you're going to need this information. So just a heads up, this is like a super important lesson, and make sure that you hang on to it. So let's get into it. Okay, so this is the lesson on types of chemical reactions as well as how to balance chemical reactions. When you're writing chemical reactions or chemical equations, you put the reactants on the left side, the products on the right side, and then there will be an arrow separating them. Now, a lot of the time you're given the reactants, but not the products. So when your products are going to be ionic compounds, still remember our rules from the naming lesson, which is when you make an ionic compound, you must cross over your charges. And even when you're given the reactants, a lot of the times you're just given the names of the reactants. So again, if it's a molecular compound, use your prefixes to figure out what the formula will be. If it's an ionic compound, you have to cross over your charges. And also don't forget about your diatomic molecules. If I just say the word oxygen, you have to know that that is O2, same with nitrogen or chlorine or any of those Hofbrinkel molecules. Balancing chemical reactions essentially means making sure that the number of atoms of each element are the same on the reactant side as they are on the product side. This is important because the law of conservation of mass tells us that atoms cannot be made or destroyed, just rearranged in chemical processes. And so because of that, we have to make sure that we're not losing or getting extras of any of our atoms of different elements. So we'll start by going through some example problems of how to balance chemical equations. Okay, so the first problem that we're given is iron plus oxygen makes iron oxide. And because we were given this in formula form, we don't have to cross over our charges or anything like that. All we need to do is balance this. And so the way we start by balancing is we divide this reaction in half where the arrow is. Then I'm going to write what elements I have on each side just as a single element. So I have iron and I have oxygen and then the same on the other side. And even if they don't come in the same order on both sides, I am going to write the elements like lined up with each other. Okay, so then on the reactant side, I'm just going to count the number of iron I have, and I just have this one here. And then for oxygen, I have 2, because this little 2 tells me that I have 2 oxygen atoms. And then on the other side, I have 1 iron here, and then 1 oxygen. And so all I need to do is make sure that these numbers are the same for my 2 irons. So that my irons are good, they're balanced, but my oxygens are not. I have to balance those. And so the only way to balance, you can never take away atoms, you can only put in more atoms. So I'm going to have to increase the number of oxygen atoms on the product side. You're also only allowed to add coefficients, not subscripts, okay? Can only add coefficients, not subscripts. What that means is I can add a big number in front of a molecule. I cannot add any little numbers. So I can't just put a 2 here and say, okay, now I have FeO2. Now, if I want to get 2 oxygen on this side, the only way to do it is to put a coefficient of 2 in front of that molecule. That 2 then multiplies to both of those elements. So because of that, I now have 2 iron and 2 oxygen. So now my oxygen are balanced, but my iron are not. Now I need to increase the number of iron on my reactant side. Again, the only way to do that is to add a coefficient, and that will multiply to my iron. The reason I'm saying multiply is because sometimes people want to put like a 1 here, and they say, well, I already have 1. If I put the number 1 here, now I have 2. But 1 times the 1 that already exists there is still just 1. So that's why I say multiply in. Okay, and now we are balanced. So that is how we balance a chemical equation. Let's try the second example here. So HCl, that is hydrochloric acid, plus Zn, which is zinc, is going to make hydrogen gas, so H2, and zinc chloride. Again, I'm going to divide this reaction in half where the arrow is, write out what elements I have on each side in the same order. And then I just count. I have 1 hydrogen here. I also have 1 chlorine, and I have 1 zinc. On the other side, I have 2 hydrogen, 1 zinc, and 1 chlorine. So the only thing that's not balanced right now is my hydrogen. I'm going to need to put a 2 here in order to get 2 hydrogen, but that also changes my number of chlorine to 2. So now I have to go over to the other side. My chlorine is here, so I'll have to put a 2 in front of that molecule in order to get the 2 chlorine. But of course, that means I also have 2 zinc. So now my last step, go over to my zinc on this side, put a 2 in front of it, and now I have 2 of everything, so it's balanced. Okay, so I just wrote out one last example for us to try here. Only slightly more complicated because it has more atoms than the ones we've just done. Again, I'm just going to split this in half where my arrow is, write out the different elements that I have in the same order on both sides. And then I'll just count. So when you have a subscript like this, it only applies to whatever is directly in front of it. So that's telling me I have 2 aluminum and 3 oxygen in that aluminum oxide. And then in my calcium chloride, I have 1 calcium and 2 chlorine. And then on the other side, I have 1 aluminum, 1 oxygen, 1 calcium, and 3 chlorine. So I've got a lot of things that aren't balanced as of right now. The first thing I'm going to start with is maybe trying to balance my oxygen. So right now I have 3 oxygen on this side. I only have 1 on the other side. And you could start with balancing your aluminum too, it doesn't really matter. I'm going to put a 3 in front of my calcium oxide. That is going to give me 3 calcium and 3 oxygen. We could also balance our aluminum, like I said. So right now I have 2 aluminum on this side. In order to get 2 aluminum on the other side, I need to put a 2 in front of the aluminum chloride, that will give me 2 aluminum, but that too also applies to my chlorine. And like I was saying previously, this multiplies in. So when I have a coefficient and a subscript both applying to an element like this, they get multiplied. So I end up with 2 times 3, which is 6 chlorine. Okay, so now my aluminum and my oxygen are balanced. My calcium are not, so I need 3 more calcium on this side here. I have to put a 3 in front. That will give me my 3 calcium. And then I have a 3 and a 2 both applying to the chlorine. They multiply together to give me 6 chlorine. And now everything is balanced. So that is my balanced chemical equation. I have just 1 aluminum oxide, 3 calcium chloride, 2 aluminum chloride, and 3 calcium oxide. Okay, now that we've gone over how to balance a chemical reaction, let's go into the different types of chemical reactions that you can see. So the first 2 are opposites of one another. That's why they're compared to each other here. The first is a synthesis reaction, also called a formation reaction, and the second is a decomposition reaction. So in synthesis reactions, we always start with at least 2 molecules, and we're going to end up with just a single product. The way that we recognize a synthesis reaction is usually because on the reactant side, we just have 1 element, so in this case oxygen, reacting with another 1 element, in this case hydrogen. So it doesn't matter that I have 2 oxygens and in this case 4 hydrogens. I have 1 element reacting with another element. So none of these are compounds, like ionic compounds or anything like that. And then decomposition is just the opposite of that. We start with only 1 molecule as our reactant. We're going to end up with at least 2 products. So the way we can recognize a decomposition reaction is because it is the only type of reaction that only has 1 reactant. The next different types of reactions are displacement reactions. And once again, there are 2 types of displacement reactions. There are single displacement reactions and double displacement reactions. The difference between these is that with a single displacement, you have 2 different molecules that are reacting. One has 2 different ions, like this sodium chloride, so 2 different elements, and one just has a single element, like this bromine here. With a double displacement, both of the molecules that are reacting are made of at least 2 elements, or 2 different ions. So we have the sodium chloride, in this case, reacting with the lithium bromide. In both types of these reactions, what's happening is either your metals are swapping places or your non-metals are swapping places. A metal can only switch places with another metal. A non-metal can only switch places with another non-metal. The only exception to that is hydrogen can sometimes switch places with another metal. And that's just because hydrogen sometimes acts like a metal. That's why on the periodic table, it's over by the metals. The next 2 types of reactions are endothermic versus exothermic reactions. So in these cases, it just has to do with the type of energy. These 2 reaction types are the only ones that you aren't going to have to be able to identify just by looking at the reactants, okay? But you do have to know that endothermic reactions absorb or use energy. So you might see energy written as a reactant. Exothermic reactions always release energy, so you might see energy written as a Another type of reactions is a neutralization reaction. This happens when you have an acid and a base reacting together and they end up neutralizing one another. In the case of a neutralization reaction, we recognize it because we have an acid and a base as our two reactants. The products will always be water and a salt of some type. In order to figure out what the salt will be, all you do is you take the H away from the acid, you take the OH away from the base, and whatever's left over makes your salt. You always write the metal before the non-metal. So we wrote the Na and then the Cl to make NaCl. NaCl won't always be the salt. When we say salt, it's just an ionic compound of some type. And then we also have hydrocarbon combustion reactions. Hydrocarbons are just compounds made of mostly hydrogen and carbon. So methane, propane, butane, all examples of hydrocarbons. When you have a hydrocarbon combustion reaction, you will always have some type of molecule made mostly of hydrogens and carbons. It will always react with an oxygen molecule. You will always make carbon dioxide and water. So hydrocarbon combustion reactions are always identical, except you're going to have different hydrocarbon molecules, but the rest of the reaction will always be identical. So what we're going to go through now is how to recognize these reactions, or how to practice recognizing these reactions based only on the reactants, and also how to predict the products. That's kind of the most important part, is using your knowledge of these different types of reactions and applying it to be able to predict your products and stuff like that. So let's practice that. Okay, so in this first example here, I have a reaction where my only product, or sorry, my only reactant is this NH3, which is an ammonia. As soon as I only have one reactant, that tells me right away this is a decomposition reaction, which means I can then predict the products are just going to be nitrogen and hydrogen. We just kind of break this molecule apart into the individual elements. So nitrogen and hydrogen. The only thing we have to remember is that nitrogen and hydrogen are both diatomic molecules. So anytime you write something by itself, just double check, is it one of those diatomic molecules? If it is, you need to put a little 2 behind it. And then this isn't balanced. You can practice balancing this if you would like, but for right now, we're just going to be identifying the different types of reactions and predicting our products. So that is one type, our decomposition. In the second type here, I'm going to do H2S and AlOH3. Now this time, you need to recognize that an H at the front of a molecule is an acid, and OH at the back is a base. And anytime I have an acid plus a base, it is going to be a neutralization reaction. In a neutralization reaction, we always make water, so that's always going to be the same. And then to figure out what our other molecule is going to be, all we do is we get rid of the H's at the front of the acid, get rid of the OH's in the base. Whatever is left over, so in this case, the S and the Al, that is going to become the salt. And all we have to do is write our metal first and then our non-metal. So Al and S. And then you do still have to cross over your charges anytime you make an ionic compound. So we end up with Al2 S3. Okay, so don't forget to cross your charges. That's an exclamation point. Okay, and then the water just comes from the H's and the OH's, the salt from our S and AL. Okay, third one here. If we have, let's say, oxygen gas reacting with sodium nitride, should be Na3N. This isn't anything special. I don't have a hydrocarbon reacting with oxygen, which instead would be a combustion. All I have is one element reacting with some type of compound that has at least two elements. When that is the case, and it's not a different type of special reaction, I would always check first to see if it is a hydrocarbon combustion. If it's not, then we have a single displacement, also called a single replacement. When that happens, we need this lone element to switch places with either of the elements in our compound. Because in this case, my lone element is a non-metal, it has to switch places with the non-metal in the other compound. So my oxygen and my nitrogen need to switch places. When I do that, I'm going to end up with the nitrogen by itself. Nitrogen by itself. And then the oxygen is going to end up with the sodium. So I'll have sodium oxide. When you do this, you do need to recross over your charges. So because oxygen has a charge of 2, I would have Na2O instead of Na3N. And also anything that ends up by itself, double check, is it diatomic? If it is, you need a little 2 behind it. If it's not, you just leave it written by itself. Okay, next one. I have C2H6 reacting with oxygen. Now this time, I have a hydrocarbon because it's made of hydrogen and carbon reacting with oxygen. That tells me right away this is a hydrocarbon combustion reaction. And hydrocarbon combustion reactions are very easy to predict the products because the products are always the same. You always make carbon dioxide and water every time. Okay, next step. I have, let's say, solid calcium reacting with nitrogen gas. This time I have one element reacting with another one element. If that is the case, it is definitely a synthesis reaction. It's the only time that I have two lone elements react together, which means all I do is squish those together. Of course, writing the metal first, so we have calcium nitride. And because this is an ionic compound, don't forget to cross your charges. So we get Ca3N2. Number 6. Let's do aluminum oxide. So that is Al2O3. And I'm going to react it with lithium chloride. Now, this time I have a compound. So it has 2 different elements at least, reacting with another compound. The only time I have 2 compounds reacting together and they're not an acid and a base is with a double displacement. The easiest way to do a double displacement is to just take your 2 metals and swap them places. You could also take your 2 nonmetals, but when you get into polyatomic ions, that becomes slightly more complicated. So I would recommend with double displacements, just always taking your metals and switching them. When you do that, the aluminum ends up with the chlorine, so I end up with AlCl, and the lithium ends up with the oxygen, so LiO. And then anytime we make new ionic compounds, don't forget you have to recross your charges. So I end up with AlCl3 and Li2O. And again, none of these that I've just drawn out here are balanced. They're just kind of showing you how to predict your products. But you could go through all of these and practice balancing them. It would be good practice. Okay, that is all that we're going to do for today. Let me know if you have any questions.